The universe whispers its most astounding secrets in the language of the very, very small. This is the realm of quantum physics, where the familiar rules of our everyday world dissolve into a sea of possibilities. Here, particles behave like waves, and waves like particles, defying our intuition and challenging our understanding of reality itself. Quantum physics is a journey into the heart of matter, a mind-bending exploration of the fundamental building blocks of the cosmos. Imagine a world where a single particle can exist in multiple states at once, where information can be teleported across vast distances, and where the very act of observation alters the observed. This is the strange and wonderful world revealed by quantum physics, a world that has captivated scientists and philosophers for over a century. It is a world that challenges our classical notions of cause and effect, of determinism and randomness, and forces us to confront the limits of our own perception. Quantum physics, also known as quantum mechanics, is the study of matter and energy at their most fundamental level. It is a realm governed by probabilities and uncertainties, where particles can exhibit both wave-like and particle-like behavior. This inherent fuzziness, this departure from the concrete world of classical physics, is what makes quantum mechanics so perplexing yet so captivating. It is a dance of possibilities, a symphony of uncertainties that orchestrates the very fabric of our universe. At the heart of quantum mechanics lies the concept of quantization. Unlike in classical physics, where energy can exist in a continuous spectrum, in the quantum world, energy is quantized, meaning it can only exist in discrete packets called quanta. This is akin to a staircase, where you can only step on specific steps, not in between. This quantization of energy has profound implications for how atoms behave and how light interacts with matter. One of the most mind-boggling concepts in quantum physics is wave-particle duality. This principle states that particles, like electrons and photons, can exhibit both wave-like and particle-like properties. Imagine a beam of light passing through two slits. Classical physics predicts two bright bands on a screen behind the slits, corresponding to the light traveling in straight lines. However, in the quantum world, we observe an interference pattern, characteristic of waves, even when we send single photons through the slits one at a time. How can a single particle pass through both slits simultaneously to create an interference pattern? The answer lies in the wave-like nature of quantum particles. These particles do not travel in well-defined paths like classical objects. Instead, they exist as probability waves, spread out over space, with the wave's amplitude at a particular point representing the probability of finding the particle at that location. It is only upon measurement that the wave function collapses, and the particle assumes a definite position. Section 4. Entanglement, spooky action. Perhaps the most bizarre and counterintuitive phenomenon in quantum mechanics is quantum entanglement. This occurs when two or more particles become linked, even when separated by vast distances. Imagine two entangled particles, each in a superposition of states like a coin spinning in the air, neither heads nor tails until observed. Measuring the state of one particle instantaneously determines the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein famously called it, has puzzled physicists for decades. It seems to violate the principle of locality, which states that an object can only be influenced by its immediate surroundings. However, numerous experiments have confirmed the reality of entanglement, suggesting that there is a deeper level of connection between quantum particles than we can currently comprehend. Section 5. Uncertainty, embracing the unknown. Another cornerstone of quantum mechanics is Heisenberg's uncertainty principle. This principle states that there are fundamental limits to the precision with which we can simultaneously know certain pairs of physical properties of a particle, such as its position and momentum. The more precisely we measure a particle's position, the less we can know about its momentum, and vice versa. This inherent uncertainty is not due to any limitations in our measuring devices, but is a fundamental property of nature. It arises from the wave-like nature of quantum particles. Just as a wave is spread out over space, making it difficult to pinpoint its exact location, a quantum particle's position and momentum are inherently fuzzy. This uncertainty is not a flaw in our understanding, but a fundamental aspect of the quantum world. Section 6. Quantum technologies, shaping the future. The bizarre and counterintuitive world of quantum mechanics is not merely an intellectual curiosity. It has led to groundbreaking technologies that are transforming our world. Quantum mechanics is the foundation of modern electronics, from the transistors in our smartphones to the lasers in our CD players. It has also given rise to medical imaging techniques like MRI and PET scans, allowing us to peer inside the human body without invasive procedures. Looking ahead, quantum technologies hold even greater promise. Quantum computers, still in their infancy, have the potential to revolutionize fields like medicine, materials, science, and artificial intelligence. These machines exploit the principles of superposition and entanglement to perform calculations that are impossible for classical computers, opening up new frontiers in scientific discovery and technological innovation. Section 7. The Uncharted Territory. Quantum physics, with its mind-bending paradoxes and counterintuitive principles, has fundamentally altered our understanding of the universe. It has revealed a world where the deterministic clockwork of classical physics gives way to a realm of probabilities and uncertainties, where particles dance to the rhythm of wave functions and entanglement connects objects across vast distances. Yet despite its profound implications, quantum mechanics remains an enigma, a puzzle with missing pieces. The quest to reconcile quantum mechanics with Einstein's general theory of relativity, which governs the realm of the very large, remains one of the greatest challenges in modern physics. Unraveling the mysteries of quantum gravity, understanding the role of quantum mechanics in the early universe, and exploring the potential of quantum technologies are just a few of the frontiers that lie ahead. The journey into the quantum realm has just begun, and the discoveries that await us promise to be as mind-boggling as the theories themselves.